Hey guys, welcome to 5.1 where we're going to talk about uniform circular motion, although I see that I wrote uniform circular motion, but I mean circular motion. It's the first video in Unit 5, and it's actually a pretty easy video, so you don't have to worry about your head spinning at the end of the video from all the hard problems. Do you get why that's a funny joke? Because your head spinning is kind of like circular motion. That's so funny. Okay, but seriously. Uniform circular motion. What does that mean? Uniform means same. Circular means, well, like a circle. And then motion means movement. So moving in a circle the same way over and over and over again. Okay. But actually specifically means constant speed. So what is speed? It's just a measurement of distance over time. So like if I say this object is spinning in a circle 5 meters per second, I'm going to say it's continually spinning at that same speed. It's not going to change, okay? However, just because speed's constant, does that mean velocity's constant? Well, the fact that I'm even asking that question should probably make you think the answer is no. Why is velocity not constant if speed's constant? Well, what's the difference between velocity and speed? Well, right down here. Velocity and uniform circular motion. Let's talk about velocity. Velocity is a vector. What does that mean? It means it has magnitude, which is the speed component, and direction, right? It's a vector. I can point at which direction speed's going. Let's take a look at an example of circular motion right here on the right. Here's your object. Okay, it's spinning in a circle at the same speed. So it's going 5 meters per second upward, then it's going 5 meters per second rightward, then it's going 5 meters per second downward, and then it's going 5 meters per second leftward. So the speed value is not changing, but what is changing? Well, the direction of the speed. First it's going up, then it's going right, then it's going down, then it's going left. And that's not exactly the only directions it's going. It actually changes direction little by little as it's turning. So it's going rightward here, but then at this point it's going, down here, and then at this point it's going down here. And so it's slowly changing direction. Kind of looks a little bit more like this diagram, where it's slowly changing direction as it's moving. Okay. So let's talk about velocity. The object's moving in a circle. So direction is changing. If direction's changing, and direction is a part of velocity, that means velocity is changing. Velocity will always change in uniform circular motion, even though the speed doesn't change. That's because the direction is changing right here. So if velocity is changing, velocity is changing always in circular motion. Because the direction changes, that means there's also acceleration, right? Well, this might kind of weird you out because normally we think of acceleration as like slowing down or speeding up. We think acceleration is a change in the value of velocity or speed. That's not always the case. Acceleration can happen even if your speed value doesn't change. So here, I'm not slowing down or speeding up, I'm changing direction. Acceleration can occur with constant speed and changing direction. We're going to talk more about that in a little bit. Right now, I want you to know that there is acceleration, okay? And we'll talk more about that later. The other thing you need to know is you need to know how to draw a velocity vector inside of a circle. The velocity vector will always point tangent to the circle. So, for example, the velocity line is tangent to the circle, so it's right there on the edge of the circle, pointing straight forward. So if I drew my object here, and I said, what's the velocity vector? It's right there at the edge of the circle, and if it's going this way, that's the velocity vector. So here's my object. So that's my velocity vector. So it's always tangent to the circle. All right, so that's velocity in uniform circular motion. Let's talk a little bit about what the objects are going to want to do when they're going through circular motion. And so that means we're going to have to talk about inertia. What is inertia? Well, inertia is just like a phenomenon that states Newton's first law. Objects want to continue doing whatever they're doing, and the only way they'll stop doing what they're doing is if a force makes them. So inertia is just when objects want to keep doing what they normally are doing. Basically, they're resisting change. They don't want to change direction. They don't want to change speed. They want to keep doing what they're doing. For example, this is a little putt-putt. Okay, castle. Here's your little putt-putt golf club. And you putt the little golf ball in there. Golf ball wants to continue going in a straight direction, the same direction with which it was going after you hit it. But unfortunately, it hits something. There's a force right here that keeps the ball from doing what it's wanting to do, right? Inertia makes the ball want to go through the wall, but it's not going to go through the wall because the wall is very thick, so instead it's going to change direction. Okay, until it hits another wall, and then it's going to change direction again. Then it hits another wall, and it changes direction again. And so it's going to go the direction it wants to go unless it hits something, unless there's a force that makes it turn. So this force is actually pushing our object inward. So my question to you is, when the ball leaves the putt-putt castle or whatever, what direction is it going to go? Well, it's going to continue to go in the direction that it was going in. So if it hit the wall here, it's going to continue to want to go in that direction. Okay? It's not going to continue going in a circle. That's not going to happen because there's no force pulling it. Remember, objects want to stay going the normal direction. So another thing to think about is if your object in a circle, if you're spinning something in a circle, right? The reason why it's constantly turning is because there's a force pulling it inward. And we'll talk about that in just a little bit. But if a force pulls it inward, then it will change direction. So it wants to go this direction. It's being pulled this direction. Guess what the resultant direction is? That's right. It's this angle. So it makes it kind of do the circle. So if it keeps being pulled inward, it kind of changes the direction a little bit so that it's going around in a circle like this. So the force, the pull, is going to pull it inward. Inertia makes it want to go straight. This force here, if there's got to be a force, then it would cause the object to change its direction. So let's talk about the things you need to know. Inertia resists change. Objects moving in a direction are going to stay moving in that same direction. And then lastly, there needs to be an inward force to continually turn or pull the object towards the center. Okay, let's talk about that inward force. That inward force is acceleration. Okay, acceleration exists as an inward force. So here's my object. If I want to pull it around, if I want it to change the direction this way, I need to pull it inward. Okay, so your force is always an inward force. We call that inward force centripetal force. Okay, centripetal force is all it is acceleration inward. Okay, I want to show you a picture here. Kind of talks about centripetal force in a bunch of different examples. Here's your car. Okay, the car is going forward. It wants to keep going forward. Inertia makes your car want to go forward. Friction is the force. It's the centripetal force in this instance that will pull your car inward when you're taking a turn. So when you're taking a turn, friction will keep your car from going straight because you turn your wheels, and now once your wheels have turned, there's friction that causes your car to go this direction. So why do you feel a pull? When you're turning the car, okay, there's an inward force here. But here's you sitting in the car. This is you sitting in the car. You don't lean this way when you turn. You lean the other way, right? So if I'm turning the car, I don't turn inward toward the car. I turn away from my turn. And the reason why is because of inertia. I want to keep going my same direction. So when a force pulls me the opposite direction, I kind of have a little bit of whiplash because of inertia. So if I'm standing here and someone's behind me and they push me forward, my body is not going to go forward initially. It's going to seem like it's going backward. And the only reason it's going backward is because my body is sitting right here. Let me do it this way so you can see. My body is sitting right here, okay, in this plane. And if you push me forward, my body doesn't want to do that. My body wants to stay. I have 5 more minutes. My body wants to stay where I'm at. And so if you push me forward, here's my neck wanting to stay. That's called inertia. And so I get a whiplash. So like with, here's another picture. A different kind of view. So here's your car. It's making a left turn. The car wants to go this way, okay? Friction is going to be pulling the car inward. So when you're turning, you're going to lean in this direction because of inertia, okay? There's not friction on your body, so your body leans this way. So there's a sensation of an outward acceleration when you're turning around, but really it's just inertia trying to resist the change. If you have two friends that are holding hands and you guys spin around in circles, which way does your head go? It doesn't go inside, it goes outside, right? So you might feel like your head's accelerating outside. But all that's happening is your head's not connected to their hands, so it's resisting the change of your hands. There's actually an acceleration inward. It's pulling my body inward in a circle, and my head is experiencing inertia. It's not wanting to go inside. So here's another example here. If you have a whiteboard right here with a tennis ball on it and you turn the whiteboard really quickly, I'm pulling inward on the whiteboard. So the whiteboard curves. But am I pulling on the tennis ball? No. I'm not pulling on the tennis ball, so the tennis ball continues going the same direction it was going. So you have to have an inward force on the tennis ball in order to keep it going in a circle. Okay, that's the conceptual part of circular motion and centripetal force. Now we're going to do some really basic practice problems using some formulas in circular motion. First formula you need to know is velocity. It says average speed. It's really average velocity. Okay, average velocity we know is distance, the change in distance over change in time. But in our, for centripetal force, we're going to use radius instead of distance. So the average velocity for us is going to be 2 times pi times radius instead of distance over time, okay, over the change in time. So this is the formula that we're going to be using for velocity. For acceleration, don't worry about this guy, we're going to use this as our formula for acceleration. It's v squared divided by the radius of the circle. And then lastly, don't worry about this guy, we're going to use these two formulas to find our net force. Most of the time, you probably won't need to use this middle one. Most of the time, you'll just use probably the one on the left, but I'm writing them both there for you if you'd like to use the middle one. So let's go get started. Okay, so this is the kind of math problems that you're going to be seeing with our circular motion video. First thing we do whenever we read a problem is we need to label everything we're given. So this is our mass. A 900 kilogram car is moving at 10 meters per second. That's our velocity. And remember, these are all uniform velocity problems, so that means the value of velocity is going to stay the same. It takes a turn around a circle with a radius of 25 meters. Determine acceleration and net force. So we're looking for these right here. So these are our formulas that I circled or I boxed in blue. We have radius, we have velocity, and so we can find acceleration using this formula. Acceleration is our velocity squared divided by our radius. So it's 100 divided by 25, and you're going to get you're not going to get 4 meters per second squared. So that's our acceleration. How do we find our net force? Well, we could use this formula since we have mass, we have velocity, we have radius, but this one's a little simpler. We have mass and acceleration, so let's just use this formula. F net is mass, which is 900, times our acceleration, which is 4. And so you get a nice big number here. You'll get 3,600. And remember, newtons is the unit for force. So that's a pretty straightforward problem. Let's do one more. Again, this is our speed formula right here. This is our average velocity formula. This is our acceleration formula. And this is our net force formula. Okay. So we have mass again. It says this halfback makes a turn on the football field. The halfback sweeps out a path that is a portion of a circle. Here's our radius. The halfback makes a quarter of a turn around the circle in 2.1 seconds. That's time. Determine speed, acceleration, and net force. Usually we're going to want to go in this order. You want to find velocity first, then acceleration, then your net force. It's generally a good idea to do it in this order. So velocity is 2 times pi times our radius, which is 12 meters, divided by time, which is 2.1 seconds. So you can just press pi in your calculator. There's a button for it, or you can do 3.14. It doesn't matter to me. Oops, I almost pressed the wrong number there. Okay, times 12 divided by 2.1. So my speed is 35.89 meters per second. It's my velocity right here. Acceleration is going to be my velocity squared divided by my radius, which was 12. So I take 35.89 squared divided by 12. And I get a very big acceleration, 107.3 meters per second squared. That's big. Okay. Then I take that, and to get my net force, I'll take my mass, which is 95, times my acceleration, and I'm going to get a really big number. For my net force, I get this as my net force. Really big number. Okay, so that's just 2 quick examples of some practice problems that you might see. This practice problem here says number 6. It's really number 1. This is a conceptual one. So I actually want you to give me a little paragraph or a couple sentences explaining. And then this problem, this is really number 2, 3, 4, and 5. These are more conceptual ones asking about direction of vector. Okay, and there's no math problems for you to solve in this, even though I did 2 on the board with you. Because they're so easy, I'm not really going to have you practice one. I want you to understand conceptually what's going on. So do these 5 conceptual practice problems, and that's it.